Hi! So in this video I want to look a little bit into the principle of operation of our radar sensor. So what I want to do is to show you the sensor, talk a little bit about the principle of operation of the sensor itself, what kind of signal comes out of the signal and how we can work with that. Okay, so then let's start with the sensor itself. So this is our sensor, that small guy here. So before I touch it, I make sure that the first thing I touch is the housing and not the pins. Why is that? Very easy, because I want to make sure that I do have the same electrical potential as the device itself, because otherwise if I would just immediately touch one of those pins, then there might be some ESD. Okay, so on that side this is the antenna grid. Here some special material, then like very similar to a PCB, or actually it is a PCB. We have this antenna on top of it. On the back side we have an enclosure, because this is high frequency stuff and we do not want it to radiate into the environment too much, and we have 3 pins. So here we have the glorious Datenblatt. So Datenblatt usually is like the data sheet. Good. So here's the English version of the data sheet, and let's first have a look at the electrical characteristics. I mean, like, of course, like if you select a new sensor, you first want to check the features and everything. But in our case, now we already know what's the purpose of that thing, so we focus a little bit on the technical data. Okay, so first important thing is the operating voltage range, which goes from 4.7 volt to 525 volts, so operational voltage is 5 volt. Supply current, not really interesting for us. Operation temperature, also not setting frequency, not really. Temperature drift, antenna characteristics, side loop suppression. Interface output voltage, this is interesting. Okay, so it says minus 300 to plus 300 millivolts DC offset. Okay, so which means that we do have a DC voltage, and on the top of that voltage we do have our actual signal. Why is that? If you think about, for example, you cannot really measure negative voltages usually with an ADC, and if you have an AC signal, then the negative portion of the signal would go actually also into a negative voltage range where you cannot measure it. But by introducing an offset, you lift that entire thing up. But I'm going to show that in a second how that looks like. And if we continue reading that data sheet, then somewhere we see, okay, the actual signal we're interested in is approximately 300 microvolt. Okay, so very, very small voltage here. And this signal has a frequency of 20 to 900 hertz. Why this is such a big range we will see in a second, but let's first talk a little bit about the principle of operation of a continuous wave radar Doppler thing. Okay, to understand the principle of operation of our radar module, and you see I already have my headset on because now this is a little bit about sound. To understand the principle of operation for that radio module, let's watch this video here. So it is about this that sudden frequency shift. This is what it's about. So how the sensor works is as follows. Imagine like one side, this is our radar sensor, and at the other side there's, for example, a human or some kind of reflector. And from this side now we're sending a continuous wave. So this is CW radar, continuous wave radar. We're sending a continuous wave in this direction, and it will be reflected from that obstacle or reflector and is coming back. So if there's no movement and the distance remains the same between the sender and the reflector, then the frequency of the reflected wave is the same as the sended, or the wave which was sent. Okay, and what is inside of this sensor, if I find it here, on the backside of this enclosure, there is of course some oscillator to generate the frequency for the wave we sent, but there's also a mixer, and this mixer will do the following. It will compare the reflected wave with the wave which was sent out, and if there is no phase shift, so which means there is no frequency shift, then the result is 0. So there's nothing happening. But now imagine the following, and this is very comparable to that video here where we have that same with sound. So the wave travels always with a fixed speed. So if one side or the other is moving, then we will have a frequency shift. And if you have troubles to understand that, then maybe search on the web for Doppler effect, where it's very nice explained. Okay, because this is really crucial that you understand this concept. So if you move closer, or the distance is getting closer, so there's movement, the frequency reflect or received by the radio module is higher. Okay, if they move apart from each other, then the frequency is lower. Everything based or the basic principle here is that the wave always travels with a fixed speed. Okay, and if you now have movement here, then this is causing a frequency shift. So maybe let's have a look again at that video, and maybe you recognize that if the car is coming towards us, then the frequency is higher, and after that, after it passes us, then it is lower. And of course, in between there is this nice high frequency to low frequency shift where it makes just like, okay? So, but this is not the topic here, all right? So this is the basic operation, and what this mixer in that sensor now is doing is that it's giving us simply that difference, that frequency difference, okay? Good, but how does that look like? Because like we want to build a device, okay, so now we understood the principle roughly, okay, there is some DC offset, but how does this actually look like, and what do we need to do with that? To make that a little bit more visual, I decided to use Ltspice. Yeah, I know a lot of people are really happy and crazy to see Ltspice, but no worries. I'm definitely not an expert with Ltspice, but I just try to make that work somehow, and it was important to me to do it from scratch. Okay, so we need a ground, and we need a power supply or voltage supply. So this is hidden in select component. Okay, we need a voltage here. We put it here. Oh damn! No. Ltspice usability king. Okay, we need to connect those, and we need to connect a net here so that it doesn't complain. Okay. Now let's configure that, go to advanced, and we go to sine wave. Okay, what do we need to adjust here? From the datasheet, remember that we do have a DC offset of 300 millivolt. We have an AC amplitude of 300 microvolt, or was it? Let me check. 300 microvolt exactly, with a frequency between 20 and 900 hertz, so maybe let's simply go for 100 hertz. We can leave the other options open, okay. And now, here we go. Let's try to leave everything default and see what it's doing. Stop time maybe 1. What's the step size? We'll see, maybe this is enough. And we want to probe that signal. Okay. This is now not really a sine wave because I think I just had two less, or not really enough samples to have like a beautiful sine, but it was just like, you know, creating one sample point here, one here. So this actually is a sine wave, but we cannot really see it. But what we can see here, which is more important, is how our signal looks like. And I mean, like now it has scaled it in such a way that that the waveform here, our AC wave, actually is filling the upper part. But if we zoom out, then we can see, okay, this is around 300 millivolts. So this is where our offset is. And on this offset now, on this voltage, we have our very small amplitude of our actual signal we're interested in, because we're mainly interested in, or we're basically interested in the AC signal. Okay, now I lost it a little bit with Ltspice, but I hope you get the idea. Yeah, if I zoom out even further and would try to scale that, you know, to, okay, I cannot zoom in anymore. Something like that, so that I would see from 0 to 3 volt, like you cannot see that AC signal at all. Okay, good. So this is what we have to deal with. Now we want to measure it. So one good approach is, like, if you have a project like that where you say like, okay, I have that radar sensor and I want to do something sensible with that, is to, especially with analog sensors like this one, is to first hook it up to a scope or whatever to see what it is doing. Okay, because it doesn't make sense to build an entire system because based on assumptions, and in the end, you know, 1 week before you want to ship it to the customer, you recognize, oh no, the signal actually is not as I thought it would be. Yeah? And of course this would be a huge problem. So my recommendation here, whenever you're dealing with analog sensors and stuff, first do some measurements. Okay, but there is a problem. And to show you the problem, I want to use my scope. I mean, like, this scope is nothing really special. It's pretty old school and cheap and hobbyist, but I think it's very comparable, or like it's doing its thing. Okay, you can see now that my voltage I'm measuring here is 500 millivolt, and now I go to the maximum, the voltage per division, and I can see that I have a voltage of only 20 millivolt per division, and I can't go further. And this is actually true for where there I wanted to be. Hi. So you can see here that we do have really a problem to measure that with an ordinary scope, because the scope simply is not sensitive enough to do that. And I mean, like, even if I now would have a better scope where this is now 20 millivolts, and to have something sensible, I would like to have something like 100 microvolt. So this is a factor of 10, 100, 200. Yeah, so I would need to have a scope which is of the better in the factor of 200. So that's a problem. So what do we do? Well, we amplify the signal. We amplify the signal, and this is also something, or this is basically one part this course is about, also to amplify the system. And before we do that and look at the signal, I first want to talk a little bit, just briefly, about operational amplifiers and what they're doing. Let's simply search for operational amplifier. There it is. Operationsverstärker. Maybe we'll have a look here. So first of all, let's have a look at this picture here. So what we can see here is that an op-amp has a power supply, so a positive voltage and a negative voltage, and of course the output can only be within the range of those two poles here, but obviously not the entire range. Okay, so but roughly the output is within the supply voltage of the operational amplifier. And then we do have two inputs, a positive input and a negative output. And what the operational amplifier is doing is that it is amplifying the voltage difference between those two poles here. And for an ideal or perfect or with, you know, like just mathematical operational amplifier, this amplification actually is infinite. If you want to learn more about operational amplifiers, just let me know, drop me an email, and we can look into the internals of that thing too. But this is a little bit out of scope. So the only thing we need to memorize, okay, the voltage difference between those two is amplified or infinity amplified and visible at the output. Usually the symbol we use for operational amplifiers comes without the voltage supply because yeah, this is not really where our focus is. Okay, let's see if there are some circuitries here. Internal. Okay. So this is, for example, one thing we could do with an operational amplifier. This is a so-called voltage follower. And this will already bring us a little bit in the direction of operation, what we can do with such a thing. Now, imagine the following. You bring in a slightly positive voltage here, okay, so in comparison to that voltage. So what will happen is that the output also will become positive and it will be fed back into the negative pole. So what this operational amplifier is doing here is that it actually works very comparable to a control loop, yeah, where this is the feedback path. Here, this is just a regulator. So what the operational amplifier is doing, because the output will become positive, also the input will become more positive until those two voltages are the same again. Okay, so this voltage here, UA, will be the same as UE. Yeah, and this is also called Impedanzwandler, yeah? So it's converting the impedance, or I don't know the English word for that, but the interesting point here is that if you have a load, for example, here, which would now try to pull down the voltage here, then the circuitry would regulate against it. Yeah, so you have a very different impedance than compared to the input itself. So for example, what you might want to do, you have a microcontroller which is providing some analog voltage, and of course that microcontroller cannot really provide a high current. So you feed it into such a voltage follower, and then on the output of the voltage follower you have a voltage which can provide some, or circuitry where you can also draw some current from that. Okay, so but this is now what we need to memorize here. The voltage which we give in here, the output will be regulated in such a way that the difference here becomes 0 again, okay, and in this case now then the output voltage would be the same as the input voltage. Okay, but now we can do things a little different, and what we do here is actually it is not too complicated, and once you understand it, I think it's very fascinating what's going on here. Instead of feeding back the output voltage directly back into the input here, what we do is to bring in a voltage divider. So what does this mean? The output here needs to be bigger, right? So that this voltage here again can become this voltage, and this is now where our amplification is happening, right? So you dampen more or less the output voltage here, and this way you can have this output voltage higher than the input voltage, and you can control the factor with this voltage divider here. So this is what it's all about. This is the principal operation of an operational amplifier circuitry. I mean, like, there are now different circuitries, what you can do with that. Let me see. Yeah, this is also interesting. But we can not only use this for static voltages or DC voltages, or like, I mean, like, this is not really about DC voltages. but it's, you know, like it's not really related to any frequencies. It's just, yeah, just resistors. But what you can also introduce here is, for example, to bring in components such as capacitors and inductance, which will change with the, or the impedance will change with the frequency you give. So if you, for example, have a look at the formula to calculate the impedance of a capacitor, you will see that this is 1 by J times omega C. So you see that the higher the frequency gets, the smaller the impedance gets. So I like to, I mean, like, this is not really true, but I like to think about those components as something like frequency dependent resistors. Okay, and this way, if this component here has a different impedance depending on the frequency, then you do have a different amplification depending on the frequency. Yeah, so you can also use operational amplifiers to cut away certain frequencies or to amplify other frequencies. Doch nun genug der grauen Theorie. So this is a German saying which means like, okay, this was now gray theory and fun, but now we want to see the real thing. So let's do that. Okay, now I hooked up the sensor to some secret amplification circuitry. I'm not going to show you because this is your task for this class, right? To develop this amplification circuitry. But I first want to show you a little bit here, like how to use the scope and what to expect out of to get out of that. As you can see, the scope currently is measuring nonsense, but okay, like this makes sense because we have very fine resolution and incredibly high time, so it will just give us rubbish. I mean, like, what we can try now is to, you know, manually try to look into that. Okay, it's not receiving a trigger. Okay, I think that already looks good. Let's maybe go for a resolution like that here. I've prepared something now. I already did that measurement and I know the value, so let's, instead of trial and error, simply apply them. Okay, so this is what I used here. Alright, good. So this is our signal as it comes out of the sensor. And what I will try now is to, you know, with my hand, try to bring in some movement. And you can see this is already very good. So I do something, I expect there should be something happening, and there is something happening. Okay, so I mean, like, of course I could now analyze a little bit with a screenshot here on the scope what this is actually doing, but we have tools for that. But this is already a very important milestone because this means that our circuitry is doing something. And if I would now see just a flat line, very bad. Yeah, but we can see something, thumbs up, good, we're on track. Now the next thing I want to do is, because we talked about the principle of operation of such a radar sensor. So the idea is, if you recall, we get the Doppler frequency, however this is called, like the frequency shift because of the Doppler effect. Okay, so to understand what we're actually seeing here, I will switch off the fast Fourier transfer, which will give us simply, you know, like on this scale down here, on the horizontal scale, we have 62.5 hertz per division. So this is our frequency down here, and for the vertical scale we have 50 millivolt per division. So this is our voltage. Okay, now let's try the following. I have that sensor and I will slowly, can you see that? My hand going back and forth. Now I will do that a little faster, and you can see that also the frequency is getting higher if I do that faster. Now I'm going to do that slow again, and you can see the frequency is lower. Trying as slow as I can do it. It's still possible, but I mean, like, my hand is not an ideal radar reflector or something. So yeah, but that's already it. I mean, like, this is exactly what we expected. We get this, or we get something measurable, which gives us an idea how fast an object is approaching our sensor or moving away from it. So that's all for now. Thanks for watching. If you have any questions, just drop me an email or write into the Moodle course. And as always, stay healthy, stay safe, wash your hands, and goodbye.